6.7 is exponential functions. In this section, we will be learning about the characteristics of exponential functions and how to evaluate exponential functions and be able to graph the exponential functions. First of all, we'll start by exponential functions. So you do have to memorize what this function is, and it's in the form of y equals a times b to the x, where a and b are non-zero numbers. So a and b could be any number except but 0. So y equals a times b to the x is an exponential function, and if you notice, the reason why this is called the exponential function is because the exponent is our variable. So to evaluate, we're going to be plugging x value in to find the y value. But in this equation, each of these parts of this function has a meaning where a always stands for our initial value. So whatever the amount that we start with, we'll go there. B is what's called a growth factor. How does the number grow, or how does it decay? So it's called a growth factor or decay factor. How does it grow? So if something doubles, b would equal 2. If it triples, b would equal 3. Later on, we'll learn how to use it with percentages. So let's say you invest money and you make 10%. Our growth factor will be 1.1. So we'll get to that later, but b is called a growth factor. The y value right here is our total value or final value. So this is our total value. So if this is what we start with, depending on how it grows or decays, that's going to be our final value. And x is what's called the number of times it grows, or we call it the number of times something grows or decays. So that's what x is, number of times it grows or decays. So let's say something doubles every month, and I want to know how much I have after a year. If it grows every month, it grew 12 times in a year because there's 12 months in a year. Okay, so we got a growth factor, a decay factor. That's being our b. X is our number of times it grows. A is our initial value, and then y would be our total final value. So y equals a times b to the x is the exponential function, because x is our exponent. So let's talk about our graph of the exponential function first before we go into some of the examples of how to evaluate and how to graph. So in this equation, y equals a times b to the x, our b value will determine what the graph will look like. Our growth, is it a growth or a decay? So if b is greater than 1, this is called a growth factor, because something grows, okay? And what that graph looks like is this. Now, when x is 0, and if I plug in 0 for x up here in this equation, b being any number to the 0 power is 1. And 1 times a is a. So my y-intercept when x is 0 is our a. So the graph will always go through whatever the a value is when x is 0. Because it's a growth value, the graph looks like this. As x gets bigger, it grows exponentially. And as x gets smaller in a negative value, the y value will also get really small. But one thing you have to know about exponential functions are that y never becomes 0. So this graph never crosses the x-axis. So depending on the a value, if a is positive, it's growing in a positive y direction. But if a is negative, it's going to grow in the negative y direction. So it's going to go, so it's going to still be very small y value, and it's going to grow as that gets bigger in the bigger y direction. So when a is positive a, the graph looks like this. Negative a, the graph looks like this. And that is when b is greater than 1. This is growing. We call that a growth factor. So when b is between 0 and 1, we call this decay, because it's decreasing exponentially. So same is true for where the y-intercepts are, because when x is 0, even though b is smaller than 1 and between 0 and 1, it's still going to cross that a value. And the way it grows in this one, because it's called a decay, as x gets bigger, the amount that we have is going to get smaller. So it's going to start out big, and then it's just going to get smaller, and it's going to get smaller, but it's never going to become 0. So y never becomes 0. Now if it was negative a, it's still decay, so y becomes 0, but it starts at a negative, big negative y value, and it's just going to get smaller, almost 0, but never 0 as x gets bigger. So this is a decay graph. So if b is greater than 1, it grows exponentially. And if b is between 0 and 1, it decays, and it decays exponentially. And with almost becoming 0 but never being 0. So when you graph today, don't ever cross the x-axis. So now let's talk about some of the examples that we're going to be doing in this part of the lesson. We're going to start by simple evaluating. We're going to start with example number 1. And we are going to evaluate a couple different functions here. First one is y equals 3 to the x. And I want to evaluate for x values for 2, 3, and 4. So we're going to do 3 different x values. If you notice, in my equation, y equals 8 times b to the x, in this case, b is 3, so that's my growth factor. And what this is telling me is I start my a being 1, since there's no a is 1. I have an amount of 1, let's say $1, and it triples. Because my growth factor is 3, b would equal 3, so something's tripling. That's what this represents. So when I plug it in, I'm going to plug in 2, evaluate, you plug it in, y equals 3 to the second power, which is 9. So then we're going to plug in the next one, y equals 3 to the third, so y would equal 27. And then we plug in the last one, so y equals 3 to the fourth, which is y equals 81. So if you notice, as x increases by 1 increments, my y values exponentially grow fast. That's why it's called exponential growth. It grows really fast. In the second example, I have a function named p of x. Remember, this is a function notation. That means that this function named p depends on whatever the x is. So p of x is equal to 3 times 4 to the x. Now, if you notice in this case, a is 3. That means I start with 3, amount of 3, and then it quadruples because my growth factor is 4, so it's growing 4 times as much. Now, in this case, they're going to give us a domain. And remember, domain are our x values. So they give us -2 and 3. So instead of giving it like this, they tell us the domain is -2 and 3. So remember, x is our domain, and p of x, which is our y, we're going to look for our range, the corresponding range for the given domain. So remember, when x is -2, so this is how you represent it. When x is -2, p of -2 is equal to 3 times 4 to the -2nd power. So we're still evaluating, we're plugging it in. And because this is a negative exponent, remember negative exponents make it move and make it a fraction. So this whole moves down and becomes 3 over 4 squared, which is 3 over 16. So when x is negative 2, p of negative 2 is 3/16. So if you notice from our graph before, when it's a negative exponent, the values become really small, and this is why. Now let's plug in x equals 3. So p of 3, when x is 3, p of 3 is equal to 3 times 4 to the third. And remember, using your order of operations, exponents first, so 3 times 4 to the third is 64, and then 3 times 64 is 192. So my corresponding range is 192. So that's how you evaluate exponential functions. On number 2, we're going to be dealing with word problems. In this example, you're going to write your own exponential function, and remember, you got to remember the format, which is y equals a times b to the x, where a is our initial value, b is our growth factor or decay factor. So we're going to start with 2 mice in a barn. So I'm going to live in a barn. I want to know if the number of mice quadruples every 3 months. I want to know how many mice will be in the barn after 2 years. Okay? So we're going to write the equation y equals a times b to the x. A being your initial value, and if you notice, 2 mice. So this will be my A, my initial value. And then mice quadruples every 3 months. So remember, B is our growth factor. So quadruple, so B has to equal 4. So y equals 2 mice, and it quadruples, so 4 to the x. Now remember, x is the number of times it grows. Well, it quadruples every 3 months. And I want to know how many mice are there after 2 years. So x is the number of times it grows. So quadruples. So remember, there's 24 months in 2 years, and we're going to divide by every 3 months, so it's going to quadruple every 3 months. Will tell me how many times it's going to quadruple. So it's going to quadruple 8 times. So we take this and we're going to plug it in. So y equals 2 times 4 to the 8th power is 65,536, and 2 times that is 131,072 mice after 2 years. And that's how you solve a word problem when you have a situation where something grows exponentially. So we did our first goal today was to evaluate exponential functions. So the last example will be to graph exponential functions. So in an example number 3, we're going to graph. And what we're going to do is, we know a general idea what the graph's going to look like. So 2 times 3 to the x. Remember, a is equal to 2, b is equal to 3. And because b is equal greater than 1, our graph is going to look like this. And the a value being 2, it's going to go through the y-axis at 2. So we're going to make a little table. X, 2 times 3 to the x, and we're going to give it our y value. So we're going to use -2, -1, 0, 1, 2. So we're going to plug it in, evaluate, 2 times 3 to the -2nd power. Remember, because this is a negative, it becomes to the bottom, so this becomes 2 over 3 squared, which is 2/9. Plug in the next number, 3 to the -1st. Same thing again, negative exponent makes it a fraction, so you move it, so it becomes 2 over 3 to the 1st, which is 2/3. 2 times 3 to the 0 power. Remember, anything to the 0 power is 1. 1 times 2 is 2. That's why it crosses the y-axis at y equals 2 when x is 0. And then 2 times 3 to the 1st. 3 to the 1st is 3. 3 times 2 is 6. And then 2 times 3 squared. 3 squared is 9. 9 times 2 is 18. So now when we do our graph, and because this is a growth, I only need mostly the top half of my x and y axis. Here's -1, here's -2, 0, 1, 2. I'm going to go 1, 2, 3, 4, 5, 6, 2, 6, and then so on. Now, if I divide this into 9 parts, because I need 2/9, I got 1, 2, 3, 4, 5, 6, 7, 8, 9. So here's 2/9, -2, 2/9. And then I want 2/3, so 2, 4, 6, so it's about 2/3. And then when x is equal to 0, y, this is 1, so this is 2. And then 1 is 6, so I'm up here. So if you notice, that's what the graph's similar to what we stated before. So here's my a is 2, so it crosses here. And remember, it's growing exponentially. And you know, this side just gets smaller and smaller and smaller, but never becomes 0. So this is what the graph looks like. And if you notice, this is 18, and you know it's just going to grow really fast up that way, so you don't have to go beyond that. So what I like for you to do in this section is when you're graphing, you may just use -1, 0, 1 for your x to make a table to give me those points. And I just want you to realize when it's a negative exponent, it makes this value even a smaller value because it's the denominator is smaller and it becomes a small value. And this is how you graph exponential functions.